that means we have now started. So good morning everybody, thank you for being here. Close the door for a second. There we go, and welcome to the course of General Relativity. It's one of my favorite courses to teach in here, because if there's really one theory of nature that stands out in aesthetics and beauty and application, it really must be general relativity. Don't tell the other physics professors that I said that. It is really, really, really true. And, well, it is really just a continuation of the course. Yeah, you have to pick a seat.
Yeah.
You can also realign it.
Yeah. There we go. Yeah. I really thought I had the thing figured out. See, it really wants to track somebody over there still. Maybe it imprinted on one of you guys. Okay, so with that, let me again wax poetic about how beautiful general relativity is. It's a continuation of the course of special relativity in period 2. So I understand many of you have followed it, because of course we recognize all of you in that sense. This course is going to be a step up. We're going to look at how does physics look when you step away from this thing called an inertial frame. That was the thing that we exclusively studied in the special relativity course. What are the rules of space and time when you stick to an inertial frame? And in this course, we're going to step away from inertial frames. We're going to go to whatever frame we want. And that is what makes general relativity general. It applies to every single coordinate frame, reference frame that you can think of, and is therefore applicable to all of nature. Now, here's the big surprise. You will find already today, and a little bit spill over to next week, that if you go to non-inertial frames, you automatically end up with gravity. So, for reasons we will discuss, yes, but the idea now is that if you know your special relativity, no gravity to be seen over there, and you simply decide to go to an inertial frame, or excuse me, to a non-inertial frame, you will find that you automatically get back gravity. So back in the day when Einstein had developed his special relativity in 1905, and he was thinking about, well, how can I make this also work in every single frame? He wasn't looking for gravity, he automatically found it. But if you think about it, what an enormous beauty that is of nature. That nature has decided that gravity is not just, some little factoid of nature that happens to be there. It has no choice but to be there. If you want nature to uphold the rules of relativity, you have no choice but to have gravity. Well, if there's anything I can bring with you today, let it be that message, and of course lots of mathematics, but that is the main idea of general relativity. You go to non-inertial frames, you pick up gravity, and that's cool. Because not only does it mean that we can now do calculations with gravity that before we could only sort of do, we can also go to any frame that we want, but it also opens up all kinds of new gravitational ideas that did not exist in the time of Newton before relativity, including the famous black holes and gravitational waves, and expanding universes and all that good stuff. So what will the course consist of? Well, general relativity is an enormously wide course with many, many, many topics within it. Yes, I've done it for 20 years now, and there's still many things that I don't know, as there is nobody. It really is an enormous field. So clearly I cannot do the full course justice, but what we will do is we will make sure that you have the necessary ingredients to pick up from there, get the basics, and be able to calculate with that stuff. So the first 3 weeks of this course, we're going to teach you what the mathematics is and exactly how it physically goes from inertial to non-inertial. Then a few weeks later, we're going to apply it to many cases. Let's see what goes. Okay. And then we're going to see what kind of extra effects we're going to pick up. So the second half of this course, so to say, is applications of our new rules of gravity. And that includes the black holes and gravitational waves and expanding universes. So that's the plan. Now when I say we, of course I don't mean just myself. You'll remember Brecht was sitting there, PhD student in our group, and half of you will have him as your tutor, the other half will have me, but we're sort of going to match it up a little. You're going to have each of us for about 50% of the time. So you'll be in very good hands with that. All right, so with that said, let's get started. There are some more details, but we will pick it up, organizational details, we will pick it up in the tutorials. First, let's just dive in immediately. And, well, I made the distinction before between inertial frames and non-inertial frames. That's the whole thing. You're going to step away from inertial frames. So maybe it's good to reactivate prior knowledge. What is an inertial frame? It's early morning, people have to wake up, I understand. But somewhere in your period 2 understanding there should still be the idea of what is an inertial frame, and especially what it is not, because there are some sort of flaky definitions floating around as well. We have to be clear. Yes, Erik?
The first law has to hold.
That is absolutely right. An inertial frame is by definition, there's no understanding there, a frame in which Newton's first law holds. It is not trivial that this is the case. We discussed this in period 2 in the special relativity case. If I have 2 coordinate systems and they happen to have a relative acceleration, and both of these frames look at an object, then that object cannot have a constant velocity in both of the frames, because there is some relative velocity there. That means in one of the 2 frames, Newton's first law will not hold anymore. There will be no forces, yet the thing will accelerate. It will see from that frame. Well, that frame is by definition not an inertial frame. Of the 2 frames, the frame in which an object, in absence of forces, goes with constant velocity is by definition an inertial frame. I might repeat myself from back in period 2. This is not a philosophical semantic distinction. Nature really makes a difference between those 2 frames. This is where the special goes to the general. Okay, so special relativity, inertial frames, general relativity, every frame. Let's recap a couple of ideas from special relativity. So we really have sort of everything blocked off and we can make a step to general. So 1, it's a good thing I went to OSA and picked up some markers. 1, tracking, yes, all right. There we go, nice and inky. Special relativity, that's inertial frames, or in other words, Newton's first law holds. In general, we will pick up in a moment. Any formulas that come to mind? It's not a test, just want to see if things are forgotten. This is a few months ago. Sorry, what's that?
The Lorentz transform.
The Lorentz transforms, of course. Right? Back then we studied that if you go from one inertial frame to a non-inertial frame, there's a set of general coordinate, not general in the sense of general relativity, but coordinate transformations between the 2 inertial frames, and those were given by these formulas, the Lorentz transforms. Please note, you should be used to this by now, that the C's are 1 in all my calculations. Otherwise there are a couple of C's floating around. You should have no difficulty putting them back. Anything else? Lorentz transforms, it tells you how much time spent in one frame translates how much time in the other, the same with the amount of distance, but that's what these do. Phil?
Minkowski space-time element.
Yes, this Minkowski space-time, the line element. Yeah? Actually, that is a combination of the Lorentz transforms. This, by the way, is one of the key things we will use to build up general relativity. The Minkowski line element. You might remember that this particular combination, again with all the C's put equal to 1, dt squared minus dx squared minus dy squared minus dz squared, is invariant. Has the same value in all inertial systems. And indeed, that is called the Minkowski line element. And we give it a special name. It's called d tau squared, where d tau is the proper time. All of this should be familiar, even maybe a few months back. Yes. By the way, why is this called the proper time? I mean, there's a combination of time and space, so why would I call this time? And why would I call it proper time, of all times, right? Everybody has their own time, why do I call it proper time? Is that still floating around somewhere in the memory banks? See, many people have that, so just for
Okay,
yes.
because in the proper time frame of reference, the events happen at the same place, so there is no x, y, z component.
That is exactly right. I mean, this statement is true in all inertial systems. So it's also true for the inertial system in which two things happening with a certain amount of time in between happen for that person at the same location. That very particular inertial frame has by definition the x0, dy0, and the z0, therefore this is the only thing that remains. So apparently the outcome of this particular combination is the amount of time as passed in the frame for whom the two events happen at the same location. So although this combination is true in every frame, you can relate it back immediately to the person in a very special frame, namely the frame in which two events happen at the same location. So it really is proper time. So, all right, anything else, special relativity-wise? Memory banks. Nothing with E's, C's, and M's maybe?
Space-time diagrams.
Sure, there's Minkowski diagrams. I won't bother to draw them, I'm very bad at it, but yes, the space-time diagrams. Yes, I sort of gave first kick.
Okay, e squared equals mc
Sure.
squared.
All right, e squared is p squared plus m squared. Again, with c is missing, place it back if you want by looking at missing units. Sure. Anyway, and there's a whole bunch of other stuff, yes. And we also did some Lagrangian physics, so on and so forth. I'm not going to repeat all of that. Of all these thingies, the key thing is really this one. Minkowski line element. It's a statement about space and time. How are space or distance and amounts of time related to each other in every frame? And the key part is that it is invariant. And if you have this statement, this combination equals invariant, you have all special relativity. Every single part of special relativity is built into this one single statement. It's extremely powerful. For instance, if I were just to give you this statement, and you never knew about the other stuff, you could derive these equations. I could ask you as a mathematical exercise, please find me the relation between prime and unprime coordinates such that if I replace these by prime coordinates and work out the algebra, I get back the Minkowski line element. And if you do that exercise, pop up, you get these. So this guy has this built into it automatically. The same with the Minkowski, with the Minkowski space-time diagrams. Because if you have these two, I did that back in one of the weeks of period 2, special relativity, one can derive the Minkowski space-time diagrams. You might even remember that if you play around with this a little more and you multiply it with C's and divide by M's and do a little bit of algebra on that, you can actually derive this equation. So this is also built into that. This is the key thing. Right? So we could have been very quick in special relativity. I just could have given you this in week 1 and just said I figure it out now for the rest of 6 weeks. Okay? Everything really is in there. The reason why I'm emphasizing this so much is that it already tells you that relativity is a space-time statement. If you know how space and time are related to each other, everything else follows. Same with general relativity. So let me foreshadow a little bit of the mathematics that we're going to pick up in the weeks to come. Yes. Mathematics here is relatively easy, yes. It's a little bit of algebra, maybe you have to take a square root because gamma. That's about as difficult as it gets, mathematics-wise. Not so in general relativity. The mathematical apparatus that one needs is called tensor algebra. Now what the hell is a tensor? This is not the place right now to give you a full definition, but I will pick this up with you as we go along. But I cannot help it, it is a more complicated construct to work on. Yes. I can foreshadow a little bit, but only a little. The real bigger definitions will come next week. A tensor, the way that we're going to use this, is a statement about space and time. And the claim here is that if you know how space and time are related, you can derive all that other good stuff. So we need an object, so to say, that allows you to contain all the information about space and time and how they are related to each other. Yes. Here's a quick and dirty way of looking at it. There's a coefficient in front here. It's number 1. Or in units it would be c squared. There's a number here too, there's a number there too, and there's a number there too. Those are -1. if I want to be a little bit quick about it, and instead of giving you this line element, I'm just as well off telling you the coefficients, so to say. I tell you, well, there's 4 coordinates. This coordinate appears 1 time in this Pythagorean theorem. The other coordinate appears -1 times, the other coordinate appears -1 times, the other coordinate appears another -1 times. And instead of me writing down this whole thing, I might as well just give you the coordinates, these coefficients, and the corresponding coordinates. That's the exact same amount of information. Grouping those coefficients all in one block, that block, I stress, this is only for now a working definition, that is what we're going to call a tensor. A block of numbers that tells you the coefficients of which space-time coordinates appear how many times in your curved space-time. And if you know those numbers, you can span up and see how curved space and time are. Yes? I will keep the thing for next week. It's a private discussion left tonight. So this is sort of the working definition now of a tensor. The block of numbers that tells you how these numbers connect in this Pythagorean theorem, so to say, of this 4-dimensional space-time. If you know those numbers, you would know this, and therefore you can derive all the rest of it. So, in order to get to the whole tensor stuff and the corresponding calculations, we're just going to build it up from scratch. So, we're going to actually ask ourselves the question, what happens if you start in the inertial frame and you're then going to make a coordinate transformation to a non-inertial frame? That means you're not going to use these. This is between inertial frames. You're going to go from an inertial frame to a non-inertial frame. What will happen with your coordinates, and at the end of the day, what will happen with this particular combination? And what we will find is that these numbers will change depending on which non-inertial frame you're in. And as we were just discussing, that new block of numbers with the coefficients then tells you the space-time properties of that new non-inertial frame. So this is why this tensor object is so important. The tensor, the thing that collects all these coefficients, is enough to write down your space-time, is enough to get your curvature, is enough to get all of your gravity and all of the good stuff and black holes and so on and so forth. This is the main object. So, I'm going to pause this for a moment. I'm going to go back to it. But I first want to show you what happens physically. So this is the mathematics we will fill in as we go along. But let's first talk about what happens to physics if you go to a non-inertial frame. We briefly discussed it back in period 2. So again, just a question. Do people remember what goes on if you go to a non-inertial frame? Physically. What do you feel? What do you experience? What does one see?
Fictitious forces.
Fictitious forces. There's Lara. Lara has a slight edge with some other people because of honors project. Do people recognize any fictitious forces? It's not a test. I want to be sure that I'm going to use phrasing that you're familiar with. If the answer is no, that's fine. I see a few yeses, a few undecided faces. It's good to go through it for a moment, yes? In fact, what I want to do is derive a fictitious force. A very famous one is, I think, of the fictitious forces, it's easiest to derive the centrifugal force. The stuff that you feel if somebody takes you by the arm and starts swinging you around a bunch. Yes, you feel pushed back in the back. That's a centrifugal force. It's also the stuff that if I were to swing my mug around windmill style, the coffee, if I do my best, will not spill out because it gets pushed to the back of that. That stuff pushing my liquid to the back of my cup so it won't spill out, that's a centrifugal force. Right? It's also the stuff that you feel when you're on a nice merry-go-round or a roller coaster or so, right? The thing that keeps you in your seat. Okay. I want to derive that one because that is a fictitious force. So key point here is if you go from a inertial frame to a non-inertial frame, you will find yourself feeling fictitious forces. Those fictitious forces are going to be gravitational by the end of next week. Right. So, let me derive that. What happens there? I'm going to do this first in a purely Newtonian setting. So just Newtonian physics, forget about relativity. We're going to come back to this in a bit. For now, this is just to reactivate your knowledge. Keep it there for a bit. In a moment, we're going to pick it up from there again. I am actually, so here's an example of a fictitious force. I'm actually going to take that example of you being swung around by something that's rotating. Now be very clear here. If this floor is an inertial frame, it isn't actually, because the Earth is not an inertial frame, but by good approximation it is. If the floor is an inertial frame and I'm going to take something on top like a disk and it's spinning around, that is not an inertial frame anymore because there's an acceleration between the thing that I know is an inertial frame and this rotating thing. Rotation is a type of acceleration. And one way to make sure that you're not in an inertial frame anymore is to accelerate yourself away from one. So a rotating disk is a very good example. So here's my disk, seen from above. Right? You're looking down on this spinning disk. It's spinning in that direction or so. And let's say that it spins around this axis here. I'm going to take two reference frames. One of them is bolted down to the floor. That's in black. So that's literally if I were to paint on this floor, which by assumption is an inertial frame, I'm going to paint a coordinate system 1, 2, 3, 4, 5, y 1, 2, 3, 4, 5. Top. But then somebody installs a disk here that can rotate. That disk itself comes with a couple of axes on. And for color coding, I will make that green. So that will be my prime frame. Yes. And the black frame and the green frame are rotating with respect to each other. Again, black by assumption is an inertial frame, green therefore is not. So, before we do the mathematics, let's look at a mass. M, there you go. And the mass M has absolutely no forces acting on it. Somebody just gave it a push and then let it go. Of course, in real practice there will be, I don't know, friction, all that sort of stuff. It's an idealized situation. That mass has no net forces on it. So that means that this mass will go with a constant velocity in a straight line. That's Newton's first law. But only in the black frame. Because black is the inertial frame, green is not. So in the black frame, this guy will move up with a velocity v, whatever initial kick I gave it, and we'll start moving up. And keep on going. Alright, now I make the situation such that this mass started at the exact same value for x prime green and x in black. Let's call that value the radius of the merry-go-round of my disk, of my rotating disk r. And now I'm going to look at the same situation one snapshot later. So I'm going to wait a second or so and then see what the situation looks like. So this is at time 0 in some unit. Here's the same situation. Here's the disk. The black coordinates have stayed the same, obviously. But since the two frames are rotating, some angular velocity omega, my x prime and my y prime are now different. The mass in that meantime has moved up. I even know how much it has moved up. It's v times the amount of time in between the two moments. So this is at time t. So the mass at this point in my setup is here now. Oh, excuse me, that's wrong. It will be here. It's not a perfect drawing, but you see what I mean. It goes straight up in the black frame, just traces the y axis without changing its x coordinate. And there we go. Then notably, in the black x frame, it would still be at location r, where it started. Right? This value, its x value is still r. In the green, it's not anymore. In the green frame, this is the amount r. No length contraction, there's no relativity going on. This literally just take your tape measure and see where the thing is. This is the distance r. That's the point that used to be over here. There's a little bit extra that it moved outward. might as well call that delta R, the amount of extra distance. Now there's no mystery going on here. It simply means that if you were to measure where the mass is, as seen from the green frame, you're the person using the green system, then a few seconds from the first snapshot to the next, you will see that, wait a minute, this mass has moved away from me. I was standing over here, I used to see it at location R, and a second later, it's a little bit further out. Something is pulling on my mass. It's pulling it away from me. That's what the person in the green frame would conclude, not knowing any better. Its measurement says, hey, something is pushing my ball out. Nothing is pushing the ball out. This is why it's called a fictitious force. There's nothing really pushing or pulling. It's just the green person trying to use Newton's law in the wrong frame. So for them, it looks as if something is pushing the ball out, pulling the ball out, even though there isn't. And it's just an exercise to find out, well, how much is this pulling then, as seen from the person in the green? Again, the person in the green sees this ball move away from him. This will be my coffee if I swing it around, trying to stick to the bottom of my mug. If I know the green person measures this amount per second, yes, delta R, so to say, and they take two derivatives of this, then clearly what they will get is the acceleration that the mass has, as seen in their frame. And if you were to multiply that with m, this m, Newton's second law, right? If you know the acceleration in the green frame times m, you should get a force. How much, according to the green people, according to their measurement, that ball has been pulled out by something or someone? Well, that exercise is very easy. I'm not going to do this in full here. I have to post it on Canvas, but it's really a standard exercise in some Pythagorean theorem, because look, there's a triangle over here. Yes? And I know this side of the triangle, it's R. I also know this side of the triangle, it's V times delta T, because that's how many meters the ball has moved upward in between the two snapshots. Given that it started with V and it stayed with V because of inertia frame. I also know this distance to continue my Pythagorean theorem. It's R plus the extra delta R. So I can write that now, Pythagorean's theorem. R plus delta R squared equals this squared plus that squared. That means I have a formula for delta R now, of which the solution will give me a delta T. So from this I can get my delta R as a function of time, take two time derivatives. That gives me how the green people conclude how much the ball has been pulled out. If you do that exercise, you will find that the acceleration, let's be consistent with my color coding now, that the acceleration along the green axis, so it will be prime. Just follow the exercise that I just sketched for you, just high school algebra, is m v squared over r. You might recognize this as a centrifugal force that you might have picked up in high school or people had you calculate stuff with before. It's not about the exercise here. I mean, you should be able to figure this out for yourself using the Pythagorean theorem and work out. Right? Solve for delta R, take two time derivatives, you end up over there. This is your, I was just about to correct myself because this is the acceleration, right? But thank you, because there's a very important point here. I didn't do this for didactical reasons, so let's see if somebody picks up so I can make a point. I actually made a mistake. Yes, this is the acceleration. And if you were then, so the green people would say, hey, this is the acceleration, and I know my Newton's second law. It doesn't hold, but they don't know it. So they multiply it with m, and then they get the force. Yes? So this is the acceleration, and the corresponding centrifugal force would then be mv squared over r. And thank you for correcting me. So here's that point that comes from this. Note, well, 2 points really. One of them is, here you can very clearly see that the centrifugal force, this one, is a fictitious force. Nothing is pushing or pulling on a ball. It's just the green people using Newton's second law where they shouldn't have. Yes, they were in the wrong frame. And if you're in the wrong frame, you see things accelerate, and then you might wrongly conclude that there's a force. That force is what we call a fictitious force. This is an example. point one. The second point, very important, is that, before I made my mistake of writing an M there, the acceleration is independent of the mass. Right? It doesn't matter if this guy over here is a bowling ball, or a ping pong ball, or a grain of dust, or I don't know, the International Space Station. It doesn't factor in to the acceleration that it gets. Right? The whole expression for the centrifugal acceleration is completely independent of object. It's only the space-time properties that go into here. Sure, when you make it a force, you multiply it with m, sure, then you're starting to put in some characteristics of the object itself, the mass in this case. But as far as acceleration is concerned, this guy is the same for every single object. Yes? That is an extremely important point here. Because do you, again, we're still in Newtonian physics now, do you happen to know of any other force of which the acceleration is independent of mass?
Gravity.
Yes. Okay. It's gravity. Right? If I were to drop two objects here, and again I'm neglecting all other forces except for gravity, then every single object close to the Earth's surface will drop down with an acceleration of 9.81 meters per second squared. Right? It's again one of these high school thingies that everybody has to learn. Even though the objects themselves have completely different characteristics, at the moment you lift them up and let them drop, all the difference is gone and everything drops down with the exact same acceleration. Acceleration due to gravity is independent, if it's only gravity, moving air resistance, all that sort of stuff. Acceleration due to gravity is completely independent of object. Fictitious force is also completely independent of object. Well, not force, acceleration. Here, I made the same mistake again. I should remove this, there you go. This is the one that I want to focus on. Okay? Now, this requires very little more than just Newtonian high school physics. I didn't use anything, not even a mathematics, it was just Pythagoras theorem. But it shows you that there seems to be, strongly suggested at least by this example, a strong connection between the fictitious force, the stuff by which you see things accelerate as seen from a non-inertial frame, and the gravitational force. Acceleration. Yes. Now, that doesn't mean they're the same though. But Einstein, 1908 or so, around that time, about 3 years after he published special relativity, realized, wait a minute, if I go from inertial frames black to non-inertial frames green, my masses, my motions of stuff will pick up accelerations, and those accelerations are the exact same type as gravitational accelerations. So Einstein thought, well, maybe those two things are pretty much the same. A fictitious force is the same as a gravitational force. Maybe this is what you do when you go from a non-inertial to inertial, excuse me, other way around, from inertial to non-inertial. You automatically get forces back from nature that have all the exact properties of gravity. This is a promise that I made at the beginning of this lecture. That is, wait, there's a strong connection that if you go from inertial to non-inertial, you're going to pick up gravity whether you want it or not. Yes. Now, there you go. Here's your course in general relativity. The rest is mathematics. I'm not joking. It's true. This is all that we need. The rest is mathematics. Am I missing something there? Is there any?
I would say the mathematics are pretty important.
No, they I agree. But as physics is concerned, there is not much else to it. There is a little bit more, because this is all Newtonian, but we know that even if you stick to inertial systems, you have to deal with this. So it's a little bit Newtonian physics and its conclusion that gravitational acceleration and inertial acceleration are indistinguishable from each other. And you have to marry it to what we already know from inertial frames, special relativity. And yes, that is very important to work out. So that's going to be the next step in our introduction for today. But the key part here is this strong connection between inertial frames, non-inertial frames, and gravity. Or the way that I like to poetically think about this, if you want, well, let's take one step back. Do you remember the principle of relativity? Again, back in period 2. It was a principle, it's called. principle of relativity. It's the principle that makes relativity. Also known as relativity's principle. Do people remember it? Yes?
Light speed is the same in all frames of reference.
That is one of them, yes. That the speed of light is the same in all inertial frames. Although you might also remember that you can also do away with that principle. That is one of them. That was how Einstein in 1905 came up with two postulates. That's one of them. That's correct. But there's a second one. The principle of relativity. Yeah, do you know what the principle of relativity is?
I should, I guess.
Yes?
Physics, law of motion,
That is correct. The laws of physics do not care in which frame you look at them. This is my loose translation of the principle of relativity. If you have some piece of physics floating around and you look at it, it obeys certain rules. If you now start looking, I'm sorry, you're my piece of physics here. Okay, okay. If at the moment, from this moment on, yes, I'm looking at you again, but now from a different frame. Sure, some things about you will change. Your velocity with respect to the exchange, your energy has changed. If I move very fast, the amount of time between you and me has changed because of Lorentz transforms. If I move fast enough still, the color of your hair will change because Doppler effect. So numbers will change, but there are combinations of numbers that will not. The rules by which your light and your energy, etc., those rules themselves will not change. That's the principle of relativity. Numbers can change, the rules will not. Now this is almost philosophy more than physics, but it simply says that nature does not care who and under what circumstances looks at it. The rules do not care. There's no super frame from which the rules of physics are true and the other ones are false. Every frame is as good as any other. In a special relativity, that's built into this acceleration point, the fact that this combination is invariant. This is what it meant, that you could go to any inertial frame. Sure, the numbers will change, like your hair color will, but the combination will stay the same. Now there's this same principle that we also want to apply in general relativity, and this is where I just wanted to say something poetic about gravity. If you want to promote this principle that the laws of physics are invariant between inertial systems, you want to promote it such that it also works in non-inertial systems, gravity has to kick in to make it all work. If you remove gravity, then clearly there's a difference between Newton's second law in the black frame and in the green frame, right? Because in one of them it would have held, the other one it would not have, unless gravity comes in to explain away the difference. So if you want to promote the principle of relativity, this guy, from special relativity to general relativity, nature gives you back gravity to make it all upheld. Gravity is nature's way of making the principle of relativity work in all systems. Well, that's my most poetic way of looking at gravity. In everyday, it just means if you drop something, it falls on the floor, okay? But this is the underlying idea there. Okay, so we're going to build in this more general principle of relativity into our mathematics. That means we have to get this idea into here. I'm going to remove this for now. Again, the example doesn't quite matter. It's just the centrifugal force that you know from your high school physics, maybe, or your classical mechanics, or Dutch people from the Binos. I'm going to remove this altogether. But do remember one thing. Centrifugal force, as we have seen, goes with the square of the velocity. Keep that in mind. It will come back in a second. The v squared is not a coincidence. All right. So how am I going to find the same idea that you get gravitational forces into general relativity, into relativity? Well, here did Newtonian me, but Newtonian doesn't work in this context, so we have to have a new starting point. So I'm going to write down Newton's first law in special relativity. Yes. Again, all the way back in period 2, we derived Newton's second law in special relativity. It was this one. And there was a gamma to the 3. Does this look familiar? yeah, sure, there's an M on the side, on this side, fine. We derived this back then. If you don't remember how that went, that's not really the goal here. You can look it up from the videos or from the books from back then, yes. This is Newton's second law. Now, by definition, we're going to make our starting point now that we are in an inertial frame. In an inertial frame, absence of forces, that means things will have no forces, go with constant velocity. Yes. So, from our special relativity, what we'll get this guy here. That's Newton's first law, special relativity. Simply says acceleration is zero. That means constant velocity. And it's really not one direction, but there's three of them. And that tells you that if you have no acceleration in three directions, that combined effect is a straight line. So we derived this all the way back in period 2. That's going to be our starting point because we're going to do the same exercise as we did with the merry-go-round. I'm going to take Newton's first law and then I'm going to get myself into a non-inertial system and then see what I end up with. And I promise you that after I've done my coordinate transformations, I'll go to my x prime frame, so to say, the other side of the equation will not give you zero anymore, give you non-zero. That non-zeroness is the fictitious force again. It's what you feel, what your masses get as an x acceleration due to the fact that you're not in an inertial frame. So that's the exercise that we have to do. But before I get to do it, well, I have to introduce some mathematics. Because it so happens that in order to make the coordinate transformation, coordinate transformations can be whatever. You can go to any coordinate system that you want, that's the general relativity. Not as in my example just now, a special one, the rotating frame. No, any coordinate system. So I have to get myself some mathematics that allows me to write down every coordinate transformation systematically. Otherwise, I'm stuck with doing, for every single new coordinate system, I have to redo the exercise. So it would be nice if we have one formalism that does it for all of them in one go. So, before I do that, let me introduce the mathematics. It makes it easier. That's sort of a first step towards tensors. Okay? So, consider the next 15 minutes maybe or so just a mathematical notation introduction, and after that is done, I can use that notation to do this exercise of changing this guy into the general relativistic version of the fictitious force. Yes? All right. Special relativity. This expression over here, dt squared minus dx squared minus dy squared minus dz squared. Again, I might as well give you those coefficients, but for now I will still write it out in full. It takes a while to write this out. I have to write down a full Pythagorean theorem. But you might remember that what I also can do is introduce a new notation, and there's nothing else to it. Looks like this. I put a Greek index on top of my dx. The Greek index is not a power, it doesn't say thingy to the power 5 or so. It literally just means I'm talking about 4 coordinates at the same time. And my Greek index lists which of those 4 I mean. Now by convention, mu0 means this guy here, time. mu1 means the first space coordinates, mu equals 2 means second space coordinate, mu equals 3 means third spatial coordinate. That's just the nomenclature that we use. And in this way, we're already a little bit more economic because we can write down 4 space-time coordinates in one symbol, this one here. Okay? Here's another piece of notation. If you have, let me introduce it as such. I wrote down this object twice. There's one of them here. I used the Greek index mu to list which of those 4 I meant. 0, 1, 2, 3. I wrote it down again. It's the same object. It's still dt, dx, dy, dz. But since the symbol mu is already in use in my one formula, I use a different Greek index. It really is the same object. Yes. So I've written down this guy twice over here, and I squeeze something in between. This object is, I hate myself now, it's a matrix. I say hate myself because it's a tensor, and a tensor is not a matrix. But I also said the full tensor stuff will come next week. So for all intents and purposes, let's call it a matrix for now, yes? And then after this lecture, erase this from memory for the rest of your life. And next week, we're going to see that there's a difference between a matrix and a tensor. But for now, to avoid difficult nomenclature, call it a matrix. It's a block of numbers. The numbers are as follows. I'm just introducing this. Again, it's stupid notation right now. It's -1, excuse me, I'm going to put a minus there. This is a 1, -1, 1, 1, 1, and the rest are zeros.
You're also missing a 0.
And I'm missing a 0. This is why we hired Brecht, yes? To correct my mistakes.
No, there's 3 on one.
This is correct, isn't it?
Like,
Yeah.
shouldn't the mu be? Yeah.
There we go. This is why we are going to hire out. Sorry guys, there is an object that I wrote down a second ago with the big gamma symbol. It's going to be the one that traces this. Just mixed up a couple of things because early and more coffee. Here we are. The idea is still the same. I'm simply introducing notation. I have a matrix. That matrix is this block of numbers, and I squeeze that matrix in between. I haven't done anything that you don't know yet. This is just the Minkowski line element again. I just introduced a new notation to write it more economically. Because now, the Minkowski line element looks like this object, which is somewhat shorter than we had before, this guy. But don't laugh, it's going to be, this is going to be our biggest friend as the course progresses. We will have objects that's going to have about up to 256 terms that you have to add all together. By that time, we're very happy to have this new notation. Right now, we're saving 4 terms into something that is only slightly shorter. If later on we have objects that has about 250 terms, and you can all condense it into one small object, that's going to save us a lot of writing time and mistakes, okay? That's, by the way, is this tensor algebra we're going to build up as we go along. Now, you might not recognize this as the same because I am leaving out one piece of information, namely something that is called, again, it's all notation, there's no new physics or even mathematics here, it's just notation. It's called the Einstein summation convention. What does it mean? It means if you have an object with a Greek index down, and you put it next to an object with the same Greek index up. Remember, a Greek index can have 4 values, 0, 1, 2, 3. If you have 1 down and 1 up in some combination, that by definition means. Yes? No, I thought you wanted to ask.
No. I was picturing in my head.
Okay, good. 1 up, 1 down. That combination, by definition, notational definition means let mu, the Greek index, run through all its 4 values, 0, 1, 2, 3. So you get 4 combinations here for every mu value of 1, and then add the results together. Yes, I will write this out in a second to show you how that works. Again, it's notation. We do the same with the nu, because there's also a Greek index down here, the nu, and there's one Greek index up. That too means let the nu's run over all its 4 values, you get 4 combinations, and add those together. So let's see how that works in this particular exercise, right? All right, so, well, let's just do it. I'm going to leave my nu as is for now. I'm just going to do this summing of the mu's combination first. All right, let's do it. There's a Greek index down, the mu, the Greek index up. the mu. That combination by notational definition means let it run over all 4 values. The first value is 0. Okay, mu is 0, and mu I'm going to leave as is for now. Then here's also mu that also then has the value 0. And I'm going to leave the mu as is for now. Yes. We're not done. The notation by definition means let mu run through all its 4 values. So there's another one. Mu can also have the value 1, so every mu has now the value 1, and again I'm leaving the mu's as is for now. And u can also run through the value 2. And it looks like this. Almost done. U can also run through its 3rd value, which is nu is 3. So that will look like this. So I use now what is called the Einstein summation convention. 1 index down, 1 up means let them run through all 4 values and add all the results together. That's what I did. I let the mu's have all the 4 values, added everything together. Sure, because of the minus becomes a subtraction, but here we go. Almost done. I have another one of those to go because there's also one nu down and a nu up, and those have to run through its 4 values each. Now before I write this down, how many terms will I, if I do this whole exercise, how many something will I get in total?
16.
Yeah, here's somebody mumble 16, didn't know where it came from.
16.
Yes. 16, 4, 8, 7, 300. Let's go with 16. Why? Well, when we did the Einstein summation convention of the mu's, I already got 4. Tuck, 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 tuck. But each of them has another 4 of these split ups by themselves. So this one splits up into 4 more because of the mu's. This one as well, this one as well, this one as well. 4 times 4, 16 terms. So if I were to write this out, there's 16 terms. Okay, that takes a while to write down, right? Unfortunately, it's not that bad in this case. Why? Well, that's just, if you want, you can write out all the 16 combinations. But let's be a little bit more clever. Because this guy over here, that is this matrix. And the first index is 0. That means we're here. This is first row, 0th row, first row, 2nd row, 3rd row. Those are the mu's. And within each row, there are the 4 numbers. Those are the mu's. Now, let's see what we have here. We have this guy, eta. The first index in this term is 0. That means the first row. Okay. The nu's are the numbers that run over those 4 values. So it splits up into 4 extra terms. But do you see that 3 of those terms are going to add 0 to the sum? Right? Because you have to take this combination and multiply with the number in front, but 3 of those numbers are 0. So do yourself a favor and don't write down the 16 combinations and then look at this combination. You can already see, no, this one is going to be 0, no need to write that guy down. So if I were to do that, just looking at this combination, then I see that the only one that I need to write down, well, which is it with u value? That's 0, right? That's the only one, the 0, 0, 1, that's the only one that adds to the total. And it adds a certain amount, namely the amount minus 1. All right? So the only one that survives out of all the u's here is u is 0, and it gets multiplied with a minus 1. Do you remember what dx0 means? That's dt, but you have 2 of them, dt squared. And there was a minus in front, and you get another minus dt squared. That's that one, right? Alright, moving on. We can play the same game here. You can manually split this up into 4 terms, or by looking at this guy, you can be a little bit more clever and say, hey, wait a minute, I'm in the first row, count from 0, that's that one. The nu's are running over these 4 values, and clearly the only one that doesn't add 0 to the whole mix is this one. That is nu is 1. So I get eta 1, 1, dx1, dx1, and dx1 is what we know as dx squared. And it gets multiplied by 1. There was a minus already in front, so I get minus dx squared, so on and so forth. Do the same with the other terms. And then I get back to where I started. Yes. This was this little detour that I promised to do with you guys. It looks like I didn't do anything, and I didn't. I made things much more complicated by this crappy notation. Yes. This is a little easier to write down. But it's only because this particular combination has to be very easy. Later in this course, we'll have objects like these, where these are not zeros and ones. There are highly complicated combinations of numbers. And nobody ever wants to write down all the 16 terms and the crappy combinations. You're better off at some point getting used to this notation, and we're going to do all of our calculations into this notation. And only very rarely, if ever, write out the whole Einstein summation convention. So it's a high price to pay right now for something as simple as the Minkowski line element. But as the course progresses, it's going to save us an enormous amount of time, and it gives all kinds of new insights. Yes? Yep. Okay. Good. So just to put names to this guy is exactly that block of numbers that I said at the beginning that tells you these coefficients. Back then, I already sort of vaguely called it the metric tensor. The object that connects space and time to each other, in this case, for this very special case of Minkowski space-time. Well, any guesses what this guy is called? A tensor that describes Minkowski space-time? Yeah, let's call it the Minkowski tensor. And I stress with this notation in the back of your mind, instead of giving you all of that stuff, we could have done period 2, special relativity, by just me telling you this object here and be done with it. Because this is equivalent to that, and from that you get all the rest. So we could have made our period 2 course very briefly neat. Just so here's the Minkowski tensor, and the rest follows. So here we are. So again, it's notational, it takes a while, and I promise you will get used to it as we go along. More notation. This object plugged into here with the summing, this Einstein summation convention, that operation of taking an upper index and a lower index and adding together, that operation, mathematical operation itself has a name. It's called a contraction. Again, it's just nomenclature, but I'm going to use it throughout the course. Contraction. So let me write down very clearly what I mean by contraction. If I have an object, A, with an index up, I'm leaving completely aside what the object physically means. And I have another object with an index down, again, leaving completely aside what physically the object means. Then, more notation. Again, just notation. Let it sink in for a moment.
The new up, right?
Yes, because I keep being sloppy, and this is why Beth is here. Thank you. If you have an object with the index up, it will look like something like this. 4 coordinates. If you have one with an index down, like we have here, again, definitionally, it means the following. Index down is by definition the same as a thing with an index up, and then with this tensor in between. That's definitional. We will see objects with an index up and down, and again from next week onwards we will go through the distance or the actual definition of the thing. Right now it's just good to have it written down. So you can see that this is this. Yes. This particular particular combination, and then the summing of this is what is called a contraction. Up index, down index, summing over each other, contraction. So this object is from now on I'm going to call the contraction of A and B. This here is a double contraction because I do the summing twice. Once over mu and one over nu. Double contraction. Alright. All of this, without any new mathematics, without any new physics, it's all just stupid notation. But in notation, it's going to be extremely worthwhile as we go along. Again, it allows us to write very complicated expressions into much smaller expressions. It also allows us to write things that are very complicated, write 4 equations, into one equation. Just put one index on top and all of a sudden you have all 4 of them in one go. That's good. Another thing that's going to be very important later is that we will prove, I'm not doing this today, but just to foreshadow why we're going to do all this trouble to write this notation, is that contractions are invariant. I'm not proving this. Next week. If you have a Greek index up and a Greek index down combination, you squeeze them together, the contraction of that combination is the same in all systems. Why is that important or interesting? It means that if you are in a theory where things look very different in different frames, you know how to make combinations that are the same for everybody. So if you're going to look for laws of physics that are the same for everybody, you know how to write them. They have to be of this particular type. Because if you manage to write your theory in this particular combination of a contraction, you know that that theory is going to be true in all coordinate systems. I'm not proving this yet. Next week, after the proper introduction of tensor, we will prove this as a mathematical exercise. For now, I'm simply saying, why are we doing this? So again, it's economical. Long expressions become short expressions. It's also economical because you can write down 4 thingies for every mu is 1, all in one small expression. And the combination of these contractions are always invariants, and that makes them extremely valuable objects in the theory of relativity. This is the key to write down theories that work in all systems. Okay, to be proven next week. All right, now with all of that, let's practice a little with this new notation and go back to the original exercise. We're going to start in an inertial system, do coordinate transformation, and find ourselves in a non-inertial system. And then my promise was that this Newton's first law is going to pick up a non-zero at the other side. The non-zero is fictitious force, and as we discussed before, that force for those people feel like gravity. They cannot distinguish that it's not. So let's do that. And by the end of that exercise, so it's both practice in this new notation as getting this key result out, we're going to end up with an equation that is going to be one of the main equations of general relativity called the geodesic equation. Okay, so here we go. All right, this is 0. That's in an inertial frame. Let's do coordinate transformation. Let's change x by some transformation into a new coordinate, x prime. This one here. And x prime, the new coordinates, are a function of the old coordinates. It's very abstract right now saying that. I'm simply saying that if I write down a coordinate system on this floor, that's my unprimed, and I start moving with respect to it, then the way that I move, my own coordinate system has some relation to the one on the floor. Highly dependent on how I happen to be moving about. So I can express my primed coordinates in the unprimed coordinates, and that's what I mean here. Note that I'm not saying what it looks like. That's the power of my result. I'm not going to specify which new coordinate system I'm in, a rotating frame or something else. That's the general. The result's going to hold for every coordinate transformation. We have to do this though for 4 coordinates because there's a time coordinate in the inertial frame, there's an x, a y, and a z, or whatever your spatial coordinates are. So I can do two things. Either I write this expression 4 times, one for time, one for x, one for y, and one for z. Or, if it so happens I have a notation at the ready, do all of them in one go. That's what I'm doing now. Those are the 4 coordinates that I had, time and 3 spaces. Then I find myself in a new set of coordinates primed, also 4 of them, so it also comes with the Greek index. And if I'm really pedantic, then I should say that my prime coordinates are a function of the old coordinates, which were also 4 of them. So I need the Greek index here too, not mu, it's already in use. So take your pick, alpha or something like that. Yes. My 4 new coordinates are a function of my old 4 coordinates. Now, notation-wise, and this is just the way that we do this in general relativity, yes, the alpha should be there, but things become very messy because I have a couple of coordinates of these indices floating around. So there's sort of this convention that if you take your 4 coordinates as an argument of a different function, right? It appears in some other function, you sort of drop the Greek index. It's there, but otherwise I have to carry both a mu and an alpha around. So it's a stupid notation to remove the notational clutter. You usually don't write the alpha there. Okay, I'm going to take that coordinate, or sorry, that's Newton's first law. I'm going to do this coordinate transformation. Okay? Actually, it's slightly easier if I do it the other way around. If I reverse the arrow. I mean, it's equivalent, yes? I mean, either I transform from this frame to the other, or from there, or from the other to me. There are coordinate transforms that will go both ways, and my exercise happens to be slightly easier if I start with my non-inertial coordinates and then move to the other. So that's what I'm going to do. Okay, well, let's just see what happens. First of all, I'm going to do this in 2 steps. There's 2 derivatives going on. I'm first going to worry about this derivative, and then I'm going to worry about the other derivative. Here's the first. My unprimed coordinates are a function of the primed coordinates. Yes, that's what this guy says. So I should be able to write this as, well, some derivative of, well, let's write it explicitly like this now. Yes. My unprimed are a function of the primed. Okay. So, suggestions. What do I do? I know that this guy is a function of primed, and I have to take the tau derivative. That guy is also a function of tau. So what do? If you have a function, and you have to take the derivative with the thing inside the function.
Chain rule.
Sorry?
Chain rule.
Let's use the chain rule. Exactly. Right. I'm simply saying this. I have a function. Just from your high school calculus, so to say, I have this function over here. And what do I do? Well, this is the same as this. Read? So I have to do the same here too. And I can use that. But there's a slight variation to the theme here. Because I have a situation here where my x without the prime is a function of not just 1 primed, it's a function of 4 of those. Right? Remember, by definition, or sorry, by convention, you don't write the Greek index on top of the inside function, but they are there. X is a function of 4 primed coordinates. So instead of having this, that f depends on x, it also depends on maybe on y, and maybe on z, and maybe on something else as well. That means you don't just have this term as your chain rule, you're also going to have this. There's no relativity here, this is just calculus. Yes. So this one, when I had only one inside coordinate, that is called the chain rule, that you might remember from high school. If you have more than one inside function, you're going to get as many of those terms as one has inside functions. It's called the generalized chain rule. So we're going to have to use that here. But this is a little crappy because our inside function over here, that's 4 of them, so I have no choice but to write down 4 of these terms because of the generalized chain rule. So it would be nice if we had a notation that sort of collapses 4 terms into one. And we do. It's called the contraction that we had before. Because look, suppose I also enter a time coordinate in here, then I get, actually let's call it, let's call it d prime. Then I get dt, dt prime, dt, df, dt. Prime, there you go. Yes? Generalized chain rule for 4 coordinates. But with our new notation that we had before, instead of writing down 4 of these, you're much better off making your life very simple. Because I can collapse all of this together by simply writing this. Let this sink in for a second. No new physics, no new mathematics, just a notation that I introduced before. Remember this. Greek index up, Greek index down means let the Greek indices run over all 4 values and then add everything together. If I were to do that over 4 Greek indices of these, x, y, z, t, t prime, right, 4 of these, you get all of these derivatives. The contraction of the mu's is going to give you each and every single of those 4 terms added together. So I'm simply saying here that the generalized chain rule that you might know from your calculus or a multivariable calculus course can also be written in this notation, in contraction notation. It saves you a lot of time in writing. Yes. So I can do the same thing here. So, help me out. What do I write? I told you, it's also an exercise in this new notation that you have to get used to. Help me out here. This function depends on a couple of these guys over there. Use this notation over here. Let it sink in for a moment. So I have a mu here, let's ignore it for a moment. This mu is a function of 4 x primes. And by generalized chain rule, that means I'm going to have to take 4 derivatives and add them together according to this rule over there. That's what I did here. This is a generalized chain rule from your basic calculus course, but simply now written